So let's continue talking about sources of magnetic fields. In the last video, I said we were going to pick up on example 28.4. So we have two sources of magnetic field here, right? We have a wire pointing out of the page, current coming out of the page. We have another wire with the current pointing into the page. And the right-hand rule is going to tell us what direction the magnetic field due to those wires will be pointing at different positions around the wire. And then what we're going to do is we're going to add those two fields together to find the total magnetic field due to those two wires. So let's flip over to a place where we can do some work, because there's quite a bit of work associated with finding the field at these two places. So I copied down the problem here, but I erased all the vectors, which essentially tells you the answer. So let's try to do it ourselves. So the first thing we're going to recognize is the magnitude of the magnetic field that each of those two wires emanates is mu naught I over 2 pi r, where r is the distance the wire is from the point that we want to know the field. I'm going to turn this... There we go. I don't know how to turn that off. Okay. So the difficult part of this problem is figuring out what direction the magnetic field is pointing at P1, P2, and P3. So let's work on P1. And let's draw the magnetic field that the wire 1 creates. So the way you figure out the direction of the magnetic field is you point your thumb in the direction of the current of wire 1. So your thumb should be pointing out of the page right now. And what you'll see is your fingers will curl in a counterclockwise direction. So the magnetic field around wire 1 will be circles where different radii correspond to different magnitudes of the magnetic field, okay? And the directionality of those circles is going to be counterclockwise. So let's draw one circle. Since we're interested right now working at P1, let's just draw one circle with a radius of equal to the distance that P1 is away from wire 1. So there's roughly a circle like that. The magnetic field is going counterclockwise. So if we draw our little arrows at the important points that we're interested in, such as P1, you can see that the tangent to that circle at P1 going counterclockwise is down, okay? So what is that? That's the magnetic field due to wire 1. Let's do wire 2 now. Since we're interested at P1, we're interested at the total magnetic field at P1, so we need to also take a look at the magnetic field that wire 2 generates. So wire 2, in order to figure out its magnetic field direction, we're going to point our thumb into the page. And by doing so, you'll notice your fingers curl in a clockwise direction. So we can draw another circle whose radius is quite large, okay? The center of that circle should be at wire 2. My circle's a little bit lopsided, but you get the idea. The radius of that circle is going to be the distance that wire 2 is away from P1, and it's moving in the clockwise direction. So if we draw our clockwise arrows, you can see that when we get to P1, let me draw that a bit smaller. When we get to P1, I'll draw it another color too. Our magnetic field is pointing up. That's the magnetic field due to wire 2. Let me draw that circle again in red. Okay, so the directionality is clockwise, right? So you can see if we follow the clockwise pattern, by the time we get to P1, we're pointing up. So we know our directions of the vectors. Let's write down our magnitude. So at P1, the magnetic field due to wire 1 is going to have magnitude mu naught I over 2 pi r, and its direction is going to be pointing down, which is in the negative j hat. So what's r in this case? R is the distance wire 1 is from P1. And if you look at the picture, it looks like we're going to do a little bit of math. 3D minus D, which is 2D. Okay. And then negative, go ahead and put the negative out there. So what about B2? B2 is going to be mu naught I over 2 pi r in the positive j hat direction. What is R for P2? Well, that's the distance that wire 2 is away from P1. And that is going to be 3D plus D, which is 4D. And so now we need to add these two vectors together to get the total magnetic field at P1. So we have negative mu naught I over 4 pi d j hat plus mu naught I over 8 pi d j hat, which gives us a total of negative mu naught I over 4 pi d in the j hat. So the overall direction of the magnetic field at P1 is going to be in the negative j hat direction. And that makes sense because wire 1 is closest to point 1. So the magnetic field due to wire 1 is going to have the most influence at that point, which we can see is negative, right? So we're adding a large negative to a small positive, and we're going to be left over with a negative value. So a little conceptual check there. That makes sense. Let's do P2. So I'm going to go back up here and get rid of these circles. Oh, there's our answer. Let me be a little more careful with my erasing. And let's go ahead and draw our circles to get an idea of what direction the magnetic field will be for each wire. So I'll do blue for wire 1. Let's draw a circle around wire 1 with radius P2, okay, or radius D. Thumb is out of the page. Fingers of your right hand will be curling in the counterclockwise direction. And you can see that the B field due to wire 1 at P2 is pointing up. Let's do wire 2. So wire 2, we're going to have a circle centered at wire 2, radius D as well. Okay, and this time our thumb will be pointing into the board or into the screen, and our fingers then will naturally curl clockwise. So what you can see is that we actually also have an up as well. And so why is that? Look at P1. P1 we had an up and a down, and P2 we have them both facing up. So what's going on? Well, if you look at P2, it's to the right of wire 1, but it's to the left of wire 2. So you have kind of opposite locations with respect to the relationship between the position and where the wire is, right? And the second thing that's going on is the directionality of each current is opposite. And so that just leads you to having two magnetic field pointing in the same direction for both wires. So we're going to have P1 and P2 pointing, B1 and B2 pointing up. Let's check the magnitudes. Well, the magnitudes are going to be equal as well because they are the same distance away from the point, okay? And then the magnitudes of the current are equal. So B1, I'm just going to go ahead and replace R with D. It's in the positive J. B2 will be the same. We add them together, and we get 2 times mu naught I over 2 pi d, which simply gives me mu naught I over pi d j hat. Let me go ahead and circle these answers so we can check them later. And let's work on the third point. So P3 is to the right of our wires. Oops. And let's draw our little circles so that we have an idea of what direction. I'm not going to be able to erase that one. So wire 1, right, its magnetic field is centered at wire 1. The radius of that is going to land on P3. Thumb out of the page, fingers of your right hand naturally curling counterclockwise. So if I draw my little counterclockwise arrows, I get an up right here. So B1 is up. What about B2? Draw a circle centered around wire 2, radius P3, okay? And thumb pointing into the board, fingers naturally curling in the clockwise, so I have a down for B2. Okay, right, clockwise. So B1 positive, B2 negative. Let's write their magnitudes down. Mu naught I over 2 pi, distance from wire 1 to P3. This is the distance here. Looks like it's 2D plus D, which is 3D. And then was it up or down? B1 is up, J hat. B2. Distance that wire 2 is from P3 is D, okay? Because this is 2D, this is D. 2D minus D is D. Direction was negative. So let's add these vectors together to get the total field at location P3. So it looks like we have a 6 and a 2. I'm trying to do some mental math here. The 1/6 is smaller, right? That's a 1 over 6. This is a 1 over 2. So 1/6 minus 1/2, 3/6. So I should get 2/6 or 1/3. So mu naught I over 3 pi D, and the negative is bigger, so I'll have a negative J hat. And that is going to be the total magnetic field at P3. So let's see if that makes sense. We have an overall negative value at P3, and that is because the location of P3 is closest to wire 2. So the contribution of the field due to wire 2 is going to be the greatest. And the magnetic field direction of wire 2 is down, so we should definitely have a negative number. So all that makes sense. All we've done is just do some vector addition, okay? Keeping track of the distances, doing the right-hand rule for each wire. Those are kind of the conceptual parts that you need to really work on in order to master this kind of problem, because something like this would definitely appear on an exam, okay? So definitely, focus on this example when you're studying. Let's head back over to the lecture slides. I want to go over a conceptual example that comes right after this. This is just a slide that, we kind of talked about it when we worked on 28.3. There's a number of reasons why when current passes through a wire, why you don't feel such a great gigantic magnetic field. One of the reasons we saw the magnitudes are just, not that high. The second thing we have going on is in each of these wires we have, each of these little black cables here, we have multiple wires in there. And that's to form a complete circuit, right? In order to get current to flow, we need a complete circuit. So even though you have one single wire, bundled inside there is going to be smaller wires that go to your device, turn around, and come back to form a complete circuit. And so therefore you have different current directions, and outside of that wire, the fields will add up oppositely, right? So you'll get a negative or a zero field outside. For example, looking at P1 here, right? P1 is outside wire 1 and wire 2. And you can see that the B field due to wire 1 and wire 2 add up or subtract from each other. And you have a small, magnetic field outside of that. So there's another reason why we don't really feel magnetic fields outside of these wires, because you have those two bundled wires inside forming the complete circuit with the current flowing in opposite directions. So that's the idea here in this slide. So let's do this conceptual example. There's a lot going on here. Okay, bringing some stuff back from previous chapters. So what we have going on here is we have a circuit, and we are using the compass to figure out what the magnetic field is above this branch. Okay, so we have this compass here placed on top of this wire. And the way we're going to get current to flow through this circuit here is we're going to plug in two batteries, battery A or battery B. The difference between them is obviously their polarity. So plugging one in versus the other is going to give you different current directions. So the question is, when you plug in one of those batteries, which one would give you a compass needle pointing this way? Okay, pointing in the light pink direction. So what is this direction here? Well, this is going to be the compass, what it's measuring before any current flows. This is going to be the direction once the current starts flowing, which battery would produce that. And so let's kind of like break it down. What is this question really asking you? It's asking you what current direction, okay, current flowing this way or current flowing this way, which one will give you a magnetic field that adds to this, okay, to create this vector. All right, so there's like many layers here. So let's start off by just reviewing what the compass does, right? How is it used to detect magnetic fields? Well, the compass points towards the direction of the nearest magnetic field. And so the magnetic field here, before any current is flowing, is showing up like this. So before we have current flowing, we have a magnetic field pointing straight north. And once the current starts to flow, in order to achieve a deflection like this, we're adding a magnetic field in this direction, which I'll call BI, the magnetic field that the current produces. So those two vectors, the green and the blue, are going to add together to this purple vector, which is the deflection. So we're going to figure out, okay, does a clockwise current produce a magnetic field pointing to the left, or does a clockwise current produce a magnetic field pointing to the left? So let's do that. Let's figure that out. So a clockwise current, that would be the red current. A clockwise current would mean that current is flowing through this branch this way, and that current is flowing down through this branch. Okay, I just drew it over here because, there's a lot of picture there. And so if we do the right-hand rule on a current flowing down, the right-hand rule we're going to do is your thumb is pointing down and your fingers are going to curl around your thumb. And where we need to stop our fingers is above the wire. So if your thumb is the wire, you want to pause your fingers above your thumb, and what you'll see is that the the magnetic field generated by the current is pointing to the left. Okay, because my fingers are paused above my thumb. If my fingers were going to go rotate below my thumb, then you would have a B field pointing to the right. But since the compass is above the wire, we care about the B field pointing to the left, which is above the wire. And well, it turns out that we picked lucky. We picked the right choice because we are interested in which current direction produces a B field pointing to the left. And so it is definitely the clockwise current. So the clockwise current creates a B field above it, above the current, pointing to the right. I'm sorry, pointing to the left. It's pointing to the left. And so why is that? Because I point my thumb in the direction of I, and then my fingers are on top of my thumb pointing to the left, okay, as they're making that rotation around my thumb. And so when you add that B field vector to the existing north, you get the purple vector, which is this one. So now the question is, which battery produces a clockwise current? Well, recall that current is the flow of positive charges. So positive charges leaving a battery would leave the positive terminal and be attracted to the negative terminal. So battery A is the battery that provides the clockwise current, and therefore your answer is battery A. Okay, so there's a lot going on here. Okay, you got to remember how a compass works. You got to remember how to hook up a battery to get the current direction that you want. You got to remember what direction the magnetic field is pointing if you are above, below, to the left, to the right of a wire, okay? A lot of stuff going on here. So this is a very good test type question where it has many layers of concept that needs to be totally mastered. So we talked about the magnetic field that wires create, okay? But if you recall, wires that carry current also feel magnetic fields and feel a force due to those fields. So we're going to combine these two ideas. The idea that wires generate magnetic fields, and therefore, if they are in the vicinity of another wire, that other wire is going to feel its magnetic field and thus have a force on it due to that field. So in this picture here, we have two current carrying wires, I prime and I, okay? And they're both carrying current in the same direction. So current I is responsible for creating a magnetic field, and we can figure out the direction of that magnetic field at all points around the wire by putting our thumb in the direction of the current and then curling our fingers around that. And what you see is this picture here with the blue vectors. Okay, if you curl your finger around the wire and your fingers are above the wire, you're going to see your fingers are pointing out of the page when you're above the wire. And then when you go below that wire, your fingers are pointing into the page. So that's what this picture is showing us. And so if we place a second current carrying wire I prime above I, the magnetic field it's going to feel is going to be in this direction. Go to my blue. Right? It's going to be in this direction coming out of the page. And so if wire I prime feels a magnetic field out of the page, we'll do a second right-hand rule to figure out the force that wire I prime feels. Okay, so there's two right-hand rules going on. Number one, so right-hand rule number one, determine B field direction created by I. Right-hand rule number two, determine force felt by I prime due to field created by I. Okay? So if we throw an X, Y, Z coordinate system on here, let me see what the best one would be, the most, go like this. Let's kind of rotate a little bit. I want to try to make it as, there we go. Let's do that. Okay. Let's say Y is up, X is here, and then Z is pointing out of the page. Okay. And what we can see here is that our current is in the X direction. Our resulting magnetic field above at the location here, our resulting magnetic field due to I is going to be in the Z direction. And then the force, so what direction would that make the force? Well, we do another right-hand rule. So let's write down these equations, right? Remember the force here is I, L cross B, and the magnetic field was doing the right-hand rule with your thumb curling around I, okay? That's where I got K hat from. So then the force is going to be I, L, I hat, cross whatever B was, all that stuff, in the K hat. I cross K is what? We can do our little I, J, K. I cross K is going counterclockwise, so that'll make it negative J. So you can see that our force is going to be in the negative J direction. That's the red vector pointing straight down, which is in the negative J direction, right? So that's kind of breaking down this picture. And so what we did is, well, we basically just computed the force that a wire feels in a magnetic field, but that magnetic field just so happened to be created by I, okay? So I acted as a source of a magnetic field, whereas before, earlier chapter, we were just given B, right? B was just there. B was like, okay, here's B. Now B is created by another wire, so we have to do a right-hand rule in the beginning to figure out what direction B is in order to find what direction force is. And so what, if you were to do the same procedure for the opposite case, where I prime is creating the field and I is feeling the force, you would end up with the same magnitude of force, but your direction would be in the opposite direction. And so we can summarize this, okay? When we summarize it, what we see is that the force that one feels due to the other, well, those, and vice versa, those force magnitudes are equal, okay? And if we scale that down by unit length, what we get is that the force is mu naught I times I prime over 2 pi r. So that's the force per unit length between two parallel current carrying conductors, okay? And so let's talk about directions of the force. This is the magnitude. Let's talk about directions of the force. Well, there's two cases to consider. The first case, let me just, oh, do I not have that slide here? Okay. Oh, well, I'm sorry, that was back on this slide. The two cases we need to consider here in order to understand the direction of the force is if the wires are carrying current in the same direction, okay, which is in the picture here. So if I is in the same direction, then the force is attractive, okay? So that means that the force direction that this wire feels will be pointing directly towards the other wire, okay? So they feel an attractive force. If these two wires were pointing in opposite directions, not pictured here, okay, but if they were pointing in opposite directions, then the force vector would, on each one, would be pointing away, and you would have a repulsive force. Okay, so that's kind of how you summarize the forces between parallel conductors. This is their magnitudes, equal for each one. Directionality determined by whether they are pointing, I is pointing in the same direction for each one, or if I is in opposite directions. So let's, this example is pretty straightforward. It's really just a plug and chug. I'll let you guys do that one on your own. Here's the work for it. So let's talk a little bit. We're kind of bringing back, I already told you about the definition of, well, not the definition. I told you about what the units are for current, right? And they're ampere. So in previous chapters, units for current are ampere. And the reason why it's being brought up again here, that's my cat sneezing, by the way. The reason why it's being brought up here is because the way we define ampere is actually through the force between two wires carrying current. So 1 ampere is actually the current that, if present in two parallel conductors of infinite length in empty space, it would be the current that results in a force of 2 times 10 to the minus 7 newtons per unit meter length, okay? That's just how current was defined. It's defined through the force between two wires. So it's just an interesting fact, okay? And that leads us to why the magnetic constant is 4 pi times 10 to the minus 7, okay? Because then when we plug in a force of 2 times 10 to the minus 7 newtons per meter, we get a value of pi, 2 pi. So Coulomb then, if you recall, is going to be the amount of charge that's transferred by 1 ampere over 1 second. So Coulomb is kind of derived from the units of ampere. So we talked a lot about the magnetic field produced by a straight wire. So now what happens if we curve that current carrying wire? Well, here's a little derivation that I'm going to spare you on, okay? You can do some integration techniques like we did in previous chapters. Well, actually, we didn't do this example where we found the electric field due to a ring of charge. Maybe some of you did it. You would follow similar procedures here to find the magnetic field due to a current ring. And if you were to do those integrations, you would come up with this as a result. So the magnetic field value right here, okay, a distance x away from this current carrying loop is this. And that's the magnetic field along the x direction. And I crossed it off here because, you won't be tested on this. This is not going to show up in the exam. But what you do need to know is this right here, the right-hand rule for determining the direction of the B field due to a current carrying loop. It's going to be very important for chapter 29. And so the right-hand rule is you curl your fingers in the direction of current, and then your thumb will be along the magnetic field direction. Okay, so you can see it's kind of opposite of the previous right-hand rule we did for determining the magnetic field due to a straight wire, right? Your thumb was in the direction of the current and your fingers curled. Well, now your fingers are curling in the current direction and your thumb is in the magnetic field direction. Okay, so it's very important to have that mastered and understood. This example is a kind of a plug and chug, so don't, worry too much about it. Do it on your own. You won't need me to explain it to you. And so magnetic field lines, the magnetic field lines are always circles around current carrying wires, even when the current carrying wire is in a circular shape, right? So essentially you're just doing the right-hand rule a whole bunch of times as you go along this wire, and what you will notice is that in the center, your fingers will keep curling down through the center of the loop, and what you find out is that the magnetic field direction in the center of a loop of current is straight, right? It's not curved anymore, it's straight. So curved or looped currents have many important technological applications because they produce a very nice, straight, uniform B field in its center. So Ampere's law, not going to be tested on that, but I will just explain briefly what Ampere's law states. It is one of Maxwell's equations, and basically, if you were to integrate the magnetic field vector around a current carrying wire, the result of that, which is very similar to a flux, okay? It's analogous to a flux. It's just a one-dimensional flux. It's the B field, adding up all the B field along a loop, okay? You have to do a special integral to do that. Well, what happens is your result ends up being equal to constant times current enclosed in that loop. So you can see the analogy there with Gauss's law, right? With Gauss's law in electric fields, we had E dot dA, so the electric fields enclosed in a surface gave us the charge enclosed over a constant, right? Well, Ampere's law states that the magnetic field added up in the loop direction gives you the current value inside that loop, where the loop is a one-dimensional being, okay? It's a one-dimensional circle. Here in Gauss's law, we were talking about a surface, but in Ampere's law, we're talking in 1D, just integrating along a circle, okay? And the result ends up being the current in that circle. So it's pretty powerful math, pretty cool physics, but I'm not going to be testing you on it, but it's just something that maybe you should just know. When we talk about Maxwell's equations and we're going to see how they all fit together, you're going to note some symmetries, and this is one of the symmetries. Really beautiful math, beautiful physics here. So it's too bad we can't spend more time on it because it's quite interesting. So that's Ampere's law. Okay, read through that if you have some interest in it. I'm not going to be talking or testing on fields of cylindrical conductors, okay? So this really wraps up chapter 28. The main, examples that you need to work on for this chapter are going to be the one we did in the beginning, and also understanding this right-hand rule, and also these basically situations where what direction is the force between parallel and anti-parallel current carrying wires, okay? So that wraps up chapter 28, and look forward to videos on the next chapter, which are very conceptually heavy, okay? Easy math, conceptually difficult. So it'll be really important to watch those videos and look at all the supporting YouTube videos that I have posted on Canvas as well.